Okay, so for this section, we're going to look at acid-base balance, and we're going to divide this into two lectures. The first one, we're actually just going to look at the basics of acids and bases, and some key clinical issues related to these. And in the second lecture, we're going to look at acid-base control during exercise. We're going to talk about the role of bicarbonate and how that plays a function in both muscle cells and in the blood, and how exercise may affect some of this. So when we talk about acid and bases, my guess is that every one of you, irregardless of what classes you have or haven't taken, if I say, hey, what do you know about acids and bases, you probably have some idea that, well, okay, there's a scale, right? I think it's like a pH scale, and something can either be more of an acid or more of a base. Water is like average, and all that's true. And so I think we all have kind of at least a basic understanding of what exactly pH and acid and bases are. But I want to give us a little bit more of a science perspective. We are going to get practical with what this is. We're going to look at some clinical applications of this. But I do want us to at least have a precise definition of what these are. So technically, when we talk about an acid, we're talking about something, a molecule compound, that tends to want to liberate or get rid of hydrogen. And what we'd often say is that because of this, these will cause hydrogen ion concentration to increase in solution. We would call these acids. And there's going to be numerous acids we're going to look at in the next lecture. Lactic acid is one of those, though certainly not the only one. It's something we've already talked about before as far as metabolism being a byproduct, potentially of glycolysis. If you recall from the Krebs cycle, there are quite a few acids that play a role in that cycle as well. So a base would be the opposite of that. A base would be a molecule compound that is going to combine with hydrogen ions. And a great example, though there are many, would be bicarbonate. Bicarbonate's a really strong base. A lot of cleaning solutions tend to be more basic. Ammonia tends to be a base. Calcium carbonate, which we see in chalk, are bases. So there are bases out there as well. And the way we measure this is with what's called the pH scale. Now, pH scale, there's a reason why it is what it is. You would think intuitively, it would be, well, if you have a lot of hydrogen ions, you'd be high on a scale, and if you have few of them, you'd be low. But it actually works the reverse of that. What the pH scale is, a pH scale, actually think of it as a power, P power, of hydrogen. And if you think of it that way, the power of hydrogen, in other words, how much hydrogen exists, is actually a function of the negative log of hydrogen ions. Now, this may take a little bit of high school science, math to remember logs. You may not want to remember them. Try to keep it simple here. This is an exponential scale. And so if you take the concentration of hydrogen ions, which in a normal solution like water is 1 in a million or so, then the pH, if you start doing math of that, would be 7. So we typically say that neutral on an acid-base scale is 7. And so anything below that 7 would have a lot of hydrogen ion concentration. It would be an acid. Anything above 7 would have a lower hydrogen concentration. That would be a base. And this scale, again, is not linear. It's a scale that's exponential. So if you have something that's a 10 on the pH scale, that's exponentially stronger than a 9, which is exponentially stronger than an 8. All right, so those are acids and bases that we'll talk about. This is sort of a picture of what some of these are. Obviously, this is not an exhaustive list of acids and bases, though you probably will pick up on a couple things just by looking at this, in that a lot of the things we think of when it comes to food, when it comes to everyday use, citric acid, vinegar, lemon juice. In fact, if we were to list all the foods you eat, usually they are going to fall on the more acidic level. Now, that doesn't make those foods bad. It's not acid bad, base good. In fact, please don't ever drink pneumonia. That would be horribly, horribly bad. But they're often the foods we tend to be a little bit more on the acidic side. Distilled water will have a pH of 7. Now, that doesn't mean you and I have a pH of 7. In fact, we'll see as we go through this chapter and some others that different parts of the body have different pHs. For example, our blood generally is about 7.3. It's actually about 7.4, to be honest, in most people's blood in normal circumstances. However, if we were to look at the fluid in your stomach, where there's hydrochloric acid, the pH in your stomach is usually very low, somewhere in the ballpark of 3. And so this pH will vary in different parts of the body depending on the cell, the fluid, what enzymes best work in those environments. And we'll get into pH and enzymes because if you recall from metabolism, when we're talking about glycolysis and Krebs cycle, something that greatly affects enzymes, how they work, is pH as well as temperature. Well, enzymes tend to have a nice pH they like to work at. Anything severely below or above that, they tend to not work well. And so not surprisingly, most enzymes in the body tend to work really nice around 7.3 or so. Some, however, like myoglobin, which is in muscle, works at slightly less, like 6. It's a little more optimal function. Okay, so as we've talked about pH, I want to get real clinical here because there are situations in which pH in the body will temporarily alter. This could be in one of two directions. This should make sense, right? Our pH may start to get too low. That's what we call acidosis. So if it gets below 7.4, 7.35, we may have a situation where the pH gets above that. So where we'd say it's alkalosis, kind of like the alkaline battery. Yes, alkaline batteries also have a high pH. That may be something above 7.45. And so we have these two conditions, acidosis and alkalosis, that could potentially occur. And both, by the way, are not optimal. They're not good conditions. Now, with this, we can actually separate these conditions into two possible causes. We're going to divide that into respiratory and metabolic. And let me kind of give some understanding of each of these and why we call respiratory and metabolic. When it comes to pH, if we want to control hydrogen ion concentration, right, we really have two ways to control that. We have two ways to get rid of or keep these hydrogen ions. One would be through breaking down or converting those hydrogen ions to something else like a gas. And this actually occurs a lot. You do it all the time. We can convert that to CO2. Well, CO2, carbon dioxide, is a gas, and we expire that. So we often say that we may have acidosis or alkalosis conditions due to a respiratory issue and an inability to get rid of CO2 respiratory-wise, or maybe we're getting rid of too much CO2. The second mechanism would be metabolic, because the second way we would get rid of hydrogen ions would be to excrete them. Well, the main way we have to excrete is through urine. Now, feces as well, but urine's the most optimal one. And so, if we are excreting too many hydrogen ions, right, therefore we're getting rid of hydrogen ions, pH is going up, that would be a metabolic alkalosis. If we have situations where we're not excreting enough hydrogen ions, we're creating a sick environment, that would be a metabolic acidosis. And so this matrix here, any four of these conditions could exist. And clinically, actually, these are all issues to understand. And I will tell you, all of you have experienced at least one of these at some point in your life. So let's look at these a little more in-depthly. Let's look at the metabolic side. So again, the metabolic side here, we're looking at, we are metabolically forming too many hydrogen ions, or for whatever reason we're forming or getting rid of too many hydrogen ions. Well, let's look at the acidosis side. This is a side that I would tell you probably all of us have experienced to some small extent, where we are producing more acids than we're unable to buffer, to deal with. And because those acids are increasing in solution and concentration, our pH will start to drop. A lot of causes this. One is producing lactic acid, which we do during exercise. So not surprising, we all can, to a small extent, create a metabolic acidosis simply from producing lactic acid. One obvious culprit for this would be exercise. Now, there are other conditions. If there is issues with the kidneys, renal failure, and our kidneys cannot clear that hydrogen ions, we can experience metabolic acidosis. Ketoacidosis, which actually, if you remember from nutrition, we talked about ketones. which is a byproduct of utilizing lipids as far as fat metabolism. Ketoacidosis can occur, and individuals on a keto diet try to get that environment, but that can drop pH. So there are some causes here that cause at least a temporary metabolic acidosis. On the other side would be metabolic alkalosis, and the one which I know every one of us has experienced at some point in our life is vomiting. If we vomit the contents of our stomach, well, our stomach has a very, very low pH. If we get rid of those contents, we're getting rid of acids. Well, what's going to happen? pH is going to increase, right? And so we, at least temporarily, will experience a metabolic alkalosis. Now, generally, it happens when we're sick. Maybe we're having a reaction to something. Maybe it's something we ate. It might be a medication. All those situations happen. Those can create a temporary metabolic alkalosis, and that can be an issue. Others would be some abuse of medications, particularly loop diuretics. Loop diuretics cause a massive increase in urine production, getting rid of urine and water. Use of antacids, alcohol, there's other things as well that may cause this issue. So we can kind of see some examples here where metabolic alkalosis could potentially occur. Okay, so let's look at the other side. Let's look at the respiratory side. The two obvious causes here are going to do with ventilation. And so the way to think about this, if we are expiring CO2, and CO2 is formed from hydrogen ions, well, if we don't breathe out enough and we can't get rid of the CO2, well, if you can't get rid of CO2, that means we're keeping it in. That means we're keeping the hydrogen ions in, and that means pH would drop. So not surprisingly, hypo, which would be less ventilation, hypoventilation, would cause respiratory acidosis. And again, we all can experience that. Give it a try. Hold your breath. Don't do it too long. But if we were to do that, we would experience a very, very, very temporary and very minor respiratory acidosis. There are clinical conditions where this occurs. Some lung issues, whether it's COPD, whether it's more of a neuromuscular disorder relating to skeletal muscle dysfunction or some nervous system dysfunction, where we're not seeing enough ventilation, not enough breathing occurring, we will experience hypoventilation, and because of that, over time, we'll experience respiratory acidosis. pH will drop. On the flip side would be the opposite of that. If we are ventilating too much, we're breathing too much. In this case, hyperventilation. Now, there are situations this occurs. If you're stressed, we hyperventilate sometimes. You've probably heard of people who hyperventilate under stressful conditions. That can cause a temporary respiratory alkalosis. There's pulmonary disorders. Another one is altitude. We're going to talk about altitude much later on in the semester. However, altitude does trigger, for various reasons, an increase in respiratory drive and an increase in breathing rate and volume for a given activity. Well, that technically is hyperventilation, and we would experience a temporary respiratory alkalosis. So I want you to grasp these matrix of clinical conditions. All four of these can be issues, not just during exercise, but in health situations. What we're going to look at the next lecture is look at, okay, so what about exercise and this? So if exercise, we are experiencing acidosis by definition, right? And that's not good because that affects enzymes which affect metabolism. How do we deal with that? How do we reverse that? Is there a way to reverse that? We'll talk about how acids play a role in exercise in the next lecture.